And so I'm going to see if I can share my screen.
Yeah.
There we go, share screen. And all right, so I'm screen sharing. You guys can see my little slide here?
Yeah, I can see it. Yeah.
I'm going to try to make it bigger. There we go.
Yeah,
so,
that's good.
I want to brief you on a really big project that we've been working on in the College of Engineering. And this started almost a year ago. So we started creating a whole series of graduate certificates, and they're all in the process of getting approved because our University Senate is the last point of approval. And so I'm going to be on these as they get approved. And I just want you to know, if you're considering taking a class, we have a whole bunch of courses being offered online by incredibly talented faculty. And I spoke about this at an earlier Husky Bites. The university was in the process of actually requiring anybody who taught anything online to go through a pretty rigorous training procedure. So our online classes, as a result, before the pandemic even started, had become kind of world-class level, just really well-designed, well-taught courses. And so we have these online offerings now combined into packages called certificates. And so these are graduate certificates. The first 7 are in the area of civil and environmental engineering. There's going to be a whole bunch more, including certificates in chemical engineering and material science and engineering, biomedical engineering, mechanical engineering, electrical and computer engineering, and I'm sure I'm forgetting some of the engineerings, but
sustainable engineering.
There you go. There's one. So I want you to know these are in the works, and so if you're considering, you know, what might I learn in the spring, I will keep you posted on these. And if you are interested in hearing more about the various certificate programs, just drop an email to engineering@mtu.edu, and because we're in the process of launching our website and all that kind of stuff. All right. So the second thing, let me just find my other set of slides.
Your sponsor, right?
Click, yes, my sponsor. All right. I don't know how to end my show. Here we go. End my show. Well, you know, you would think I would be good at this at some point. All right. Am I still sharing?
Not yet.
No.
My slides. Okay.
Have to stop share and then reshare.
All right. So share screen.
Yes.
This is why we get started earlier, so that you can have an on-time start, Dave. All right, present. Okay, so thank you everyone for joining us for Husky Bites. It's always an honor to be with you. This is a webinar series started in a pandemic. We're still in a pandemic, and so we're keeping going. I do want to sincerely acknowledge tonight's sponsors, who are Mike and Trisha Crosby. These are every Monday at 6, and we have, I believe, 4 more ending December 8th following this. We try to always make these also go on Facebook live stream. We had one glitch so far, but they are always posted afterwards, and so you can record them, share them, etc. And so now it is my huge pleasure to introduce my co-host, Dr. Felix Adom, who came to Michigan Tech in 2008 from Ghana to earn his PhD, graduated in 2012 with his PhD, Dr. Adom in chemical engineering. He then went off to Argonne National Labs and worked for about 4 years there, if I have it correct. After which he joined Shell, the company, in 2016, where he is a carbon strategy analyst. And so Dr. Adom earned his degree working under the tutelage of David Shonnard's group. And so I will leave it to Felix to introduce Dr. Shonnard, and just thank you, audience, for joining us. It's awesome to see we have 95 attendees, and it's my pleasure every evening to be here. So thank you for joining us.
Janet, thank you for the warm introduction. Very much appreciated. So I think what I also want to do in the next minute or two is to introduce our presenter for the session. I think a few people have had a chance to shape my career trajectory at this point, right? The man I'm about to introduce is a person who saw the potential in me when I joined Michigan Tech, and he took me under his wings and he equipped me with the skills and the values that has enabled me to contribute to my current field. He is, this is indisputable, a very renowned expert in environmental life cycle analysis, sustainability-related issues, and then bioprocessing engineering as a whole. So to everybody on this call, it is my greatest pleasure today to introduce our presenter, Dr. Shonnard, a chemical engineering professor who is also the director of the Sustainable Future Institute. Dr. Shonnard, my pleasure, and over to you.
Well, thank you so much, Felix. You know, it's great to connect with students from my past, and you know, other than exchanging emails at Christmas time over the last few years, this is really a great opportunity to kind of catch up and see all the great things that you've done. And so I really appreciate that introduction. And so I guess this is the time I can share my screen and we'll go through the PowerPoint presentation that I've prepared. And then I guess, Janet, we have some time at the end for questions and answers, right?
We sure do. And the tradition is we call a hard stop at 7:15.
Yeah.
so we can eat our dinners or whatever.
No problem.
Yeah, sure.
I'll be ready to quit by then for sure. So yeah, thanks for everyone for attending. I see we're up to 111 attendees now. So maybe I can wait a couple more minutes, and there's still, this seems like the votes, you know, that are just trickling in. But I'll share my screen, and
Sure.
you know, what I want to do is to present a little bit of an introduction to the topic of plastic waste. And let's see, I'll share the, go into presenter mode here. There we go. And hopefully everyone can see the big screen here.
Mm-hmm.
Yep.
All right. So the title of my presentation is Waste Plastics Are Taking Over the World. The Solution is Circular. Now I know that probably sounds very sensational, and these photographs here are not, they're probably the worst that we can possibly expect anywhere around the world in terms of waste plastic. But you know, it's a title that was suggested to me by one of my good friends here who working with me in preparing for this presentation. And so, you know, out of deference to her, I wanted to keep it. And I think it's a very, you know, good, catchy title. But hopefully plastics are not taking over the world if we can create a circular economy for plastics. So with that, there's a quick outline here. First, I'll provide a short introduction to the different types of plastics. And then there's a project I want to talk about with two undergrad students. We went out hunting for waste plastics on a beach in Lake Superior. Motivated by the photographs from the first page, we wanted to know, gee, is it that bad in Lake Superior? And we'll find out whether it was that bad or not. And then I want to talk about the plastics on a global scale, give some sense for the magnitude of the plastics and plastic waste issue. Then introduce circular economy for plastics as a possible solution to the plastics waste problem. And specifically focusing on pyrolysis as a chemical recycling process for conversion of waste plastics back to useful materials back to plastics again, actually. And then I want to just end with acknowledgements of students. So I have a PhD student honor roll that I've prepared for the last slide before the questions. Okay, so we have, I guess, a poll here, right? So
Yeah.
This is the first question we have.
Wait a minute. You haven't taught us anything yet. We just have to know this?
Well, I want to know what my audience knows coming in.
Okay.
So we want to take a vote here. Our milk jug, is it polyethylene terephthalate? Is it polypropylene, high density polyethylene, and low density polyethylene? And
so this is where, if you don't know the answer, you just wait and see, you know, what becomes the more popular answer, and then you do that one, right? And
right.
You're sort of right.
We're seeing.
I'm going to vote for C.
Yeah, it's a good idea. That's the right answer.
Good choice.
So yeah, hopefully everyone didn't run off to the refrigerator and cheated or Googled online. I'm hoping that you just answered it to give us a truthful gauge for that.
Well,
So,
and Sue, I can see that Sue has another poll queued up, which is kind of who is joining us today. And if Sue, if you can deploy that, I'm really curious to see who is joining us today, because it varies, you know, depending on the department who's the speaker. So if you're able to do that, here we go. All right, who's joining us today? Are you a future student, meaning you might attend Michigan Tech someday? Are you a Michigan Tech student currently? Are you a graduate of Michigan Tech? Are you faculty and staff here? Are you a friend of Michigan Tech? Are you family, or are you a curious person? All right, and so this is very interesting because I want to point out that we have actually really high attendance tonight, and I do take attendance, and I do know who attends. And we have a huge number of Michigan Tech students here tonight, Dave. So I don't know if somebody required this in their class or what, but there's 38 Michigan Tech students.
I appreciate that if they did. Yeah.
Did you, Dr. Shonnard, did you?
No, I did not, but.
Yeah, so we have 7 future students, 38 Michigan Tech students, 45 graduates of Michigan Tech, and then assorted smaller numbers in the friends and family and curious people and staff.
Great.
Right.
All right. I'm gonna stop interrupting you, David. I promise.
All right. No, this is interesting to see this by background. Yeah. Okay. So I guess I can close the poll on my screen. So that's So my next slide is really, if I can get it working here. Yeah. The next slide shows the correct answer. It is high density polyethylene. So most of you recognize that. Okay, so that's just a quick background on plastic types. Now, I want to cover some of the outcomes of this study that we did on the beach of Lake Superior. So we, in the summer, a couple of summers ago, I and two of my undergraduate students from chemical engineering who wanted to help me in the lab that summer, I asked them if they would join me to go out onto a beach in Lake Superior to hunt for waste plastic. As I said, I had read and seen a lot of photographs on the web and so forth about how all the waste plastic that's washing up on our shores in the oceans and on rivers. And so here we are at the south shore of Lake Superior, the largest by area freshwater freshwater lake in the world. And so I wanted to know what the problem was out there. And so we chose this site specifically because it's close to a river. So you see the Gratiot River enters here. And we know from prior studies on ocean plastic that a lot of the ocean plastic comes down major rivers in China and Southeast Asia and so forth. And that makes it into the oceans. So this could be another avenue for plastic waste to enter the Great Lakes as well. So we chose this site. It's the Gratiot River County Park. It's located at this point in the Keweenaw Peninsula, shown as this landmass jutting out into the south shore of Lake Superior. And it's a relatively remote location.
Put the cursor on Michigan Tech while you're there.
Okay, Michigan Tech is right here on the I guess the Portage Canal. And so this is just north of, by about maybe 20 miles north of Michigan Tech. And so we found 5 sites spaced 1,000 feet apart. And at each of the sites, we had 100 feet of beach to comb and search for waste plastics. In addition to finding waste plastics on the sand or the pebbles of the beach, we also dug down into the sand to see if we could find any buried plastics or microplastics. And so we wanted to understand what types of plastics we found and the concentration and also kind of understand how the plastic got there, the dispersal mechanism. So this is the second poll question. How much waste plastic did we find on the beaches? A, more than the dirty beach on the title slide. B, about the same. And C, lower than the dirty beach on the title slide. So I think we'll have time to take that poll before finding out the answer.
Well, and somebody asks, can you vote for more than one? And I think you can. I think you can vote for more than one. So you should try it and let me know what the answer is.
But I don't think you should on this question. But
Sue, you want to go ahead and launch that poll if you can find it? I know what I want to answer, but you know.
I know what I want to answer too.
Here we go. All right, so go ahead and I want an experimental person to vote for 2 just to see what happens. How would you know if your vote counted more than once though? I don't know. It's kind of like the election, right? That's what they were spending all the last time doing, was making sure people didn't vote for more than once.
Right, exactly. Yeah. So it
all right,
looks
you have a clear winner.
It looks like lower than the dirty beach on the title slide, and that is the correct answer.
Yeah.
Fortunately, that is the correct answer. So we actually had a hard time finding any waste plastic on the beach. Actually, we did. So these pictures were taken on the morning that we walked down that beach, by about a mile down that beach, and you can see, you know, it's just a nice, pretty nice, pristine beach.
Yep.
Occasionally, we would come across a piece of plastic that was washed up from the lake. They look pretty beat up, suggesting that they spent some time out on the beach and getting beat up by the crashing waves and so forth. But yes, fortunately, it was a pretty pristine. And so this is a picture of what we found. So we wanted to know what kind of plastics these were. So here we have this green bag that looks like it's a fibrous plastic bag. And here's a part of a fishing rod, actually a polycarbonate fishing rod. This looks like it came off of a washing machine, or we're not quite sure what that was. But we found film-like materials and small bits of plastic, this white and different colored plastics that, you know, you become accustomed to seeing when you see plastic littered about. And in total, over the 5 sites, we summed up almost 1 kilogram of plastic waste. And there was no significant trend based upon the distance from the river mouth, so that there wasn't a strong correlation there. Most of the plastic was less dense than water once we actually measured its density. And we didn't find any microplastics in the sand. The sand, when we burrowed down into it, was clean. And interestingly, we found most of the samples up at the tree line. So it's at the border between the forest and the beach. And this strongly suggests that these were carried in by wave action, and the strongest wave would cast the plastic actually up into the forest at the boundary of the beach. So that's kind of the mechanism that we decided upon. It was the wave action of the beach. Based upon where we found the samples, most of them were actually up in the tree line. And the next slide shows an example of the characterization that we took part. And so in the upper left is what we call a chemical signature that we obtained from pyrolysis, gas chromatography, mass spectroscopy. And this signature is very indicative of polyethylene. And each of these peaks is 1 carbon apart. And as you go from left to right, we increase by 1 carbon number here. And so this is a very strong evidence that this is polyethylene. And we didn't subject all the waste plastic samples to this kind of analysis, but we did detect polypropylene and polyethylene and polycarbonate from the 3 samples that we did sample. And by and large, mostly there was polyethylene and polypropylene that we found on the beach. Okay, so that's what we found. Fortunately, the beach was fairly clean. We had to hunt a lot, but we did find obviously too much waste plastic for I'd like to see Lake Superior as clean as possible. So please be careful and don't litter. So now I'd like to pivot a little bit and talk about the global plastic waste issue. And so I have some slides here kind of showing some statistics and some trends. And this first graph shows the annual production of waste plastic. From the 1950 was when the first year when plastics were first commercialized, out to about 2015. So we see an exponential growth in the generation of waste plastic over that period of time as plastic production ramped up. And the different colors represent the different types of plastics. And I'll start here at the bottom, the far right corner, we see the polyethylene plastics and polypropylene, which together comprise about 50% of waste generation. We see significant amounts from polyethylene terephthalate, your soft drink bottles, and other types of plastics that we see here in the upper part. Polystyrene, PVC, polyurethane foams, polypropylene, and additives. These are going into automotive parts primarily. And actually, the waste generation is slightly lower than the production at the same year. And so that's because a good part of the production of plastics doesn't end up in the waste stream because of its lifetime during use. And so this graph on the right is shows cumulative data over the last 50 or 60 years. And the total amount of plastics that have ever been produced sum up to about 9,300 million metric tons. And the vast majority of it is in non-fiber plastics. And a small fraction is in fibrous plastics that go into textiles and clothing and carpeting and things like that. As we move down the graph, and the width of these arrows represents the magnitude of the tonnage in these different types of plastics. But you can see here that, again, the polyethylene, polypropylene are about 50%. And the rest of them comprise smaller fractions of the total production. In terms of the sectors for consumption of these different plastic types, by far packaging is the majority. 39% of all the plastics that have ever been produced have been used in packaging. And another significant part is in building and construction, but we also see a lot showing up in transportation and automotive applications, electronics, and other consumer applications. An interesting thing to note here is the lifetime that we see in each one of these applications. For example, in packaging, the average life of plastic in packaging is about half a year before the plastic ends up in the waste stream, whereas in building and construction, it can last for several decades. So this time frame is very important to consider when we think about when the plastics will actually end up in the waste stream relative to when they were produced. And so over the life of all plastics produced, we see about 5,700 million metric tons going into the waste end-of-life treatment processes. And a vast majority of this is 80% is landfilled or littered in the environment. Only about 12% is incinerated for energy recovery. And then only about 9% has ever been recycled. That goes back into the in-use stock reservoir of these materials. And so it's interesting to note also that plastics production require about 4% of annual petroleum production and another 4% of petroleum to provide the process energy requirements. And this is in addition to natural gas, which is also used as a feedstock for many plastics. So plastics really utilize a lot of resources from the environment and are managed at the end of life mostly through landfilling and not much recycling. However, these global data are one snapshot, and we can see differences, for instance, in the European Union, particularly the countries with landfill bans shown within the red box, a higher proportion of waste of plastic that is recycled, even over 40% in Norway, for example, here. But across the board, it averages about 30% of plastics is recycled. And the remainder
What do you mean by a landfill ban?
Well, these countries cannot send any of their household waste to a landfill or their commercial waste. And so they have to find other uses, recycle the material or incinerate it for energy recovery. And so we see a large proportion of these countries actually recover energy from the combustion of waste plastics. And so this makes sense in Europe, where there's not a lot of fossil resources, that they would actually use this material for energy rather than rely on imports into their economy. However, the countries outside of the landfill bans, they do rely on landfilling to a greater and greater degree, as you can see by the red portion here of these countries. And so these countries look similar to the US on average, where they rely mostly on landfilling and far less on recycling. So the European Union in general recycles 31% of their plastic, landfills about 27%, and then recovers energy about 42% of the waste plastic is treated at the end of life in those ways. Now, coming back to the United States here, let's look at the states around the Great Lakes here, the US EPA Region 5. So the states are Michigan, Minnesota, Wisconsin, Illinois, Indiana, and Ohio. And the overall recycling rates across these states vary quite a bit, from a high of 42%. And this is for all materials, not just plastics, but paper and packaging and plastics and steel and aluminum and everything, to a low of about 15% in Michigan. So let's think about the plastics recycling rate across these states. And so the next and final poll will be, are the recycling rates of plastics in Region 5 states higher, about the same, or lower compared to the global average of 9%?
This is another one of the ones where I want to wait and see what everybody else is answering.
Yeah.
We have a lot of very smart people here.
In case they're right, you know.
Right. And so the correct answer actually is winning here.
Which is that we are lower.
Which we are lower.
Yeah.
We're lower than the global average. So come on, America, we can do better.
Dang it! I know.
Yeah.
So actually, yes, because we have such low landfill tipping fees, it's actually cheaper to landfill than it is to recycle. Whereas in European countries, for example, it's very high, costs are very high to landfill. And in fact, in some of the countries, it's impossible to landfill. It's just against the law. So that's one of the reasons that we have such low recycling, because it's more economical to actually landfill it. However, the state of Michigan recently has mandated much higher recycling rates. And so I think there's a target of 25% in Michigan by the year 2025. So we'll see if that policy mandate is going to increase recycling rates. But we still need more technology to help close the loop on these materials. And so the remaining portion of my talk really is about what role does technology play in achieving this more circular economy for plastics. So here you can see that uniformly across all of the states, the recycling rates for plastics are in the single digits. Now, just one more point before I pivot is, we have had an international trade in waste plastic, and this diagram is meant to show all of the export of waste plastics from the developed countries into China. China used to be, before the ban, used to be the largest importing country for waste plastics. And then because of the national sword policy that they implemented in 2016, China is no longer accepting these quantities of waste plastics anymore. And so we can see over the year 2017, the dramatic decrease of the export of waste plastics from the European Union into China. As we go from left to right, we can see that this shrinkage from 163,000 tons of waste plastics from the EU into China to just 12. So over a 90% reduction. whereas and a dramatic decrease in Hong Kong accepting the waste plastics. But other countries have made up some, Malaysia, Vietnam, to take in those plastics. But even those countries are starting to ban them. And so it'll be on the developed countries to find solutions to close the loop and recycle these plastics. Now, finally, this is a projection out to 2050. If current trends hold, we will see the total amount of wastes that have ever been generated will exceed 25 billion metric tons over that over the whole time period. And we project to see more incineration and recycling and less reliance on disposal globally. But even with these favorable trends, we expect by 2050, unless we really turn this around, there will be more plastics in the ocean than fish by 2050. And currently the rate of annual rate of waste plastic into the oceans is 8 million tons per year. So this gives some idea of the severity of the problem and the urgency to find solutions. So why do we have this
just a clarification
problem?
question, Dr. Shonnard?
Yeah, sure.
Yeah, the trend, I thought it was interesting, the incineration overtakes, as you call it, recycling. I was wondering whether we know the driver for that. Why not the other way around? Do we know what is driving why incineration? Is it because of cost?
I think so, and because plastics are very energetic and they can be converted into energy. So that's the cheapest and most well-known and technologically feasible approach for recovering. Now, it's not a true circular economy, right? For plastics, we're not converting waste plastics back to plastics again, but we are recovering some beneficial value from the energy content of the plastics.
That makes sense. Yeah.
So why do we have this problem, this global problem of waste plastics? And really it's because we have a linear economy for plastics. That means take, make, and waste plastics. We take resources from the environment, we make plastics, and then at the end of life, predominantly we end of life treat them by waste management. And so this means that we have a tremendous economic loss of over $100 billion a year of just the embodied value in these valuable materials, frankly, that are just simply being buried or thrown away or burned. And so many in the sustainability area have proposed a circular economy as a solution to this plastic waste problem, where at the end of life, instead of having a no value to these materials and actually having a cost to society, we have technologies that can add value to these materials. And so there's actually, instead of a cost, you can actually be paid for providing these waste plastics to the conversions that can repurpose them and convert them back into plastics again. So really the key is, what are these processes that will enable this circular economy? And so the next couple of slides are meant to kind of provide that information. So in the current linear economy, the main processes involved are extractive processes, taking petroleum and natural gas from the earth, and then refining those into feedstocks that can be converted into resins by petrochemical facilities. And then these plastic resins can be converted into plastic parts, plastic products, which consumers use. And then these end up in the end-of-life treatment systems in terms of waste collection and then landfilling. And there's some reliance on incineration processes to recover energy, and very little reliance on recycling processes in this linear economy. Now, a circular economy would rely much more on end-of-life materials recovery facilities to segregate the waste plastics from the other materials in the recycling stream, from the paper, from the packaging, from the aluminum cans and glass. And then taking the plastic types and then either mechanically recycling them or chemically recycling them. Both of these can work together to close the loop. And then take the resins that are recovered by mechanical and chemical recycling and make new plastic out of them in this circular fashion. So if these processes in chemical recycling and mechanical recycling and materials recovery facilities are more economically competitive than the primary extraction, then there's a possibility that this circular economy can actually work. And so one of these chemical recycling technologies is called pyrolysis. And pyrolysis is a very well-known phenomena. And anyone who's had a campfire or a fire in their fireplace knows about pyrolysis, because the high heat that's generated in the fireplace pyrolyzes the wood into vapors, and then those vapors are combusted when combined with oxygen. And so we want to do the same thing with the certain types of plastics like polyethylene. When we apply heat in the absence of oxygen and over a certain period of time, we can break down this large complex polymer into its component pieces. And when we do this in a engineered fashion, we can actually predict the kinds of products that we can produce from this pyrolysis. And so in our research here in my lab, we've developed a two-step thermal pyrolysis where we have a primary pyrolysis step followed by a secondary pyrolysis step. So we can take plastics such as you see here, polyethylene or polypropylene, and we can have a very short and intense primary pyrolysis step to create these higher carbon number waxes. And then these in the vapor phase would continue to break down through secondary reactions to give us the products that we want: liquid fuels, gases, aromatic compounds. And so we have actually done these kinds of experiments at the very small scale that we call micropyrolysis. So we're looking at very small samples on the order of about 500 micrograms, which is very, very tiny. So you can see a small sliver of high density polyethylene here, and the size of it is on the order of a few millimeters. And we've adapted a commercial pyrolysis unit with this vapor phase pyrolysis reactor. So we generate the vapors as we normally would in this pyrolysis unit, and then the vapors travel down this pyrolysis reactor, and we can control the temperature and the vapor residence time in this secondary reaction section. And so we conducted a few years ago a series of experiments at different temperatures from 625 Celsius to 675 Celsius, and varied the vapor residence time from 1.4 seconds to 5.6. And we conducted a factorial experiment design with duplicates, and we measured the trends in the products that we produce. Now, first of all, these are kind of the fingerprints of polyethylene, as I showed you before. But if we have very low temperature and short residence time, we generate mostly these higher carbon number products. But with very high temperature and long residence time, we generate mostly these gaseous products and aromatics. And so we took all the data and compiled it. And we see this distribution of products from the pyrolysis of high density polyethylene. And so at each of these temperatures, we vary the resonance time, and we see kind of a very predictable trend to the data, where as we increase the vapor resonance time at each temperature, we see a diminishing amount of these liquid products and these higher carbon number products. And we see a higher generation of the gaseous and low carbon number liquid products, and also aromatics. And so what we've found at the micro scale is that we can tune the reaction conditions to produce the products that we want. If we want monomers like ethylene and propylene, we can operate at very high temperature and long residence time. If we want to generate more aromatic compounds, which have actually high value, we can operate at higher temperatures and higher residence times. Now, what does this mean if we scale these micro scale experiments up? Well, this diagram at the top really represents how we envision a commercial realization of this kind of conversion, where we can take these polyethylene and polypropylene waste bales that we can purchase at low cost and convert them through pyrolysis, very targeted pyrolysis, into a number of products, either monomers, which fetch a very high market price, or maybe these light hydrocarbon liquid intermediates that would be feedstocks for petrochemical facilities, which could also be then converted into polymer resins to make plastics again. Or we could convert them into more heavier hydrocarbons that might be used as fuels. So the point is, with the control of temperature and vapor residence time, we can make a range of products that would have definite market value and have the potential to close the loop and make plastics again. And so these are just some pictures recently taken in my lab of my PhD student and I working on a 1 kilogram per hour pilot plant in which we can very closely control the temperature and the vapor residence time and produce these liquid products from these types of plastics. And these are very nice fuel. These have very nice fuel or lubricant properties, or they could be very nice feedstocks into petrochemical conversion to plastics again. So hopefully, I just want to provide some acknowledgements before taking questions. Financial support from the Mexican Council for Science and Technology and the National Science Foundation and the Richard and Bonnie Robbins Endowment. And then this is the honor roll that I was talking about earlier. Some of my PhD students that have recently graduated and gone on to illustrious careers at the national labs, universities, faculty positions, both here in the US, but also in Thailand and in Mexico. And I didn't have enough room to include all my PhD students, but I certainly want to acknowledge their contributions to my program over the years. And so thank you very much for your attention and for your questions and for the polling. And if there are any further questions, I'd be happy to take them now.
Well, so thank you so much, Dr. David Shonnard and co-host Dr. Felix.
You're very welcome.
Adom. I am going to share my screen. And while I do that, I encourage people to, I know our people already have, but I would like people to load up questions in using the Q&A feature. So you could type them in. We're going to start answering questions. Thank you, audience, for joining us. You had a really like huge attendance, Dave. I don't know what you did. I'm pretty sure you made your students attend or something like that. All right.
Yeah,
so
I've done that. Yeah. Coercion.
So
maybe Dr. Shonnard Wells. Sorry,
I was going to say, well, once again, thanks for the sponsorship of Mike and Tricia Crosby. And the next session, so again, people are loading up their Q&A. The next session is going to be our own Professor Bill Endres, who's going with recent graduates and soon to graduate next week. They're going to be talking about pivoting during the pandemic from COVID to codes, which talks about some of the research they were doing. I want to point out after that, there's 3 additional upcoming sessions. We're going to end by a discussion of snow, but before that's going to be climate modeling. And we have a very famous alum, Marty Lagina, who is one of the people who created Curse of Oak Island with co-host Chair Bill Predabon, and that's going to be during Thanksgiving week. So I'm going to stop sharing and I'm going to turn it over to Felix to make a few remarks, and then we're going to handle the Q&A.
Yes, I mean, one thing that I thought is maybe for the benefit of our audience, Dr. Shonnard, if you can comment on, because what we are trying to do in the circular economy is to reduce waste as much as possible, right? So I guess what I think I'm trying to get a reflection from you is the pyrolysis process, does it produce waste? And if so, what do you do with the waste?
Well, the pyrolysis process, on our experiments so far, Felix, have found very little residue when we pyrolyze the material. Now, that doesn't mean in a commercial application where you might have contaminants coming in, maybe a dirt or other things like that, you might generate some char and some of those things. But even if you did generate some carbonaceous char, it might still have some energy value. So you could still combust that waste from the pyrolysis process. If you say you had 5–10% of the waste plastic that goes into pyrolysis comes out as this char, then it still has a lot of energy value. And so we can still extract valuable energy from that. And then if there's any mineral or ash residue from that combustion of that char, then that would have to be dealt with in some other way. Maybe you could bury it in roadways or do something like that, so you didn't have to landfill it. So there's kind of a cascade going on here with, you know, first of all, you want to minimize the amount of char that you might produce from the pyrolysis. But then even if you do, think about, well, what could be beneficial ways of using that?
Yeah, thank you for that. I have a couple of questions, but Janet, tell me if maybe it's good to look at the audience's comments first, and then maybe I think that's better.
So we've got about 24 questions loaded in the Q&A, but Felix, you can be one of the people asking. So you should ask Dr. Shonnard a really hard question that you couldn't even answer.
No, don't. Don't take revenge on me now.
I'll try not to.
Waited 8 years for that.
No, I'm not trying. The other thing I thought is really important, because normally we are looking at these technologies, we look at scalability, we look at cost, and then we look at things like carbon footprinting, right? So, I mean, what I'm thinking about is you are coming up with different products from the pyrolysis. Now, in terms of greenhouse gas savings and the benefits to existing benchmarks, can you shed some light to our audience, if that's okay, Dr. Shonnard?
Yeah, thank you, Felix. That's, as you know, all my students, in addition to their research in the lab, they also are conducting environmental life cycle assessments. So they're looking at the carbon footprint of the technologies that they're developing, right? You did it. All my students are doing that. So in terms of this pyrolysis process, one of my students, Ulysses Gracita Alvarez, just recently graduated and is now working at Argonne, following in your footsteps, sir. He did conduct a techno-economic analysis of the pyrolysis process, and at commercial scale, and he did find a positive net present value, even with, you know, recovering monomers, you know, with very energy intensive, you know, gas recovery trains and all of that, you know. So he did really a very rigorous job. And then even the carbon footprint found a favorable result. But one interesting thing that he did find is that the carbon footprint was very much reliant on electricity and the grid for the electricity. So, you know, because we have lots of compression steps in recovering ethylene, for example, right? It requires a lot of electricity in that train, right? So if we locate the facility in a very green grid, say on the Northwest where they have lots of hydropower, then we get a very good result. Or even in like New England, where they have a low carbon footprint for their grid. But if we locate it in like West Virginia, nah, it doesn't work very well.
Wyoming, not good.
Not Wyoming, not West Virginia, because they rely on coal, right? I mean, they're producing a lot of coal, they're burning a lot of coal. So
it's really interesting. Well, and very, you know, it's awfully interesting. And so for the students out there, polymers or plastics are made from, you know, hydrocarbons, right? So they're made from, you know, fuel, they're made from oil, right? And so oil can be used to make energy, or we can make polymers out of them. And then after making polymers out of them, we can use them again, right, to make energy or other polymers. So it's very, 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 I was fascinated by your talk. So
thank you.
Couple quick points and comments. So we have Sid Bratkovich, who points out that they deliver milk in glass bottles. I'm just going to point that out.
And reuse them. I hope they reuse them, right?
Well, if you don't bring your bottle back, you kind of wasted your money as a consumer. So, you know, that's a good thing. Dan Ryan asks, do people swim at that beach?
Not unless you're crazy, because the water temperature is super cold. But yes, people will swim in Lake Superior beaches, but typically the very shallow sandy beaches, because they kind of, the shallow sand kind of acts like a solar collector, and that does warm up the temperature just enough to make it tolerable. But no, I don't swim in Lake Superior typically. not a good idea.
I do.
Well, you're very brave.
Okay.
Dan Schmidt asks, did you take samples below surface in the tree line area? Great question.
Actually, yes, we did. And we didn't find any buried sand even up in the tree line, suggesting that these are lighter than water plastics that are just being deposited at the surface. And they're less dense than the sand. So even if they start to be incorporated into the sand, just they will come up to the top because of their density. You know, even if they are buried, just due to the agitation of the sand with subsequent wave action, they'll work their way up to the top. I think that's a well-known material processing separation technique. So you apply that same thinking to the sand and you end up with them coming up and not being buried.
Well, and Eric Peterson speculates, I would think lightweight plastics on the beach could be blown by the wind far into the wooded areas.
They could. So we do have both wave action and also wind action that would blow them up off the beach and into the forest. That's correct.
But that was not part of the samples, was it, Dr. Shonnard? Just clarifying that.
We did sample into the forest just a little bit to where we could see the effect of the wave action inside the forest, you know, with depositing debris up in the forest. And we found, you know, washed up wood pieces from just natural trees that are being, you know, washed in, but also plastic up there.
Okay.
Well, and Cynthia Hodges out there. Hi, Cynthia. She says, great talk. You pronounced the river in a French way, but in Michigan, I've only ever heard it anglicized to Gratiot. Is it pronounced differently in the Keweenaw? And also, what can be done to help with plastic recycling in the Copper Country?
Well, great questions. I'm not a linguistics expert. I probably just got lucky in pronouncing it correctly, but I don't know if Janet knows the answer to that pronunciation question. I certainly don't, but I think it's Gratiot. I think I may have heard it that way and then just kind of picked up on it. But
in French, wouldn't it be Gratiot?
Maybe, yeah.
I don't know.
But to answer the second question about, you know, what should we do? We do have recycling programs here in the Keweenaw, especially in Houghton and Hancock. And, you know, I encourage everyone to recycle because it's better for the environment. And just to get in, I should also mention that we are going, the state of Michigan is going to fund the first materials recovery facility in Marquette County. And so the state is investing in infrastructure here to take our recycled materials and segregate it into the different types of recycled materials. And that will be over in Marquette. Currently, Houghton and Hancock ship their recyclable materials to northern Wisconsin, near Eagle River. We won't have to ship it that far anymore. We can transport it maybe 75 miles to near Marquette. So that will reduce the amount of environmental impact in long distance transport of the recycled materials.
Well, and Felix, we have so many questions out there. We have 28 open questions, so please feel free to select a question.
Yes. Yeah, I just wanted to add, I mean, at least from the industry perspective, what is happening is there's a lot of talk around, you know, certain targets sectorally. What I mean by that is you showed a chart where, for example, the packaging industry seems to be the largest consumer of, you know, some of these products. So I think it wouldn't be a bad idea to start considering, you know, some sort of targets or, you know, that industries can work towards, because I think it's going to be, the industries can do as much as they can, but, you know, we also need to purchase recyclable materials too, I think. So something to consider as well. Yeah,
I think you drive the point, Felix, that it really is not just one industry actor alone, you know. It's the community who wants to recycle. It's the policies that can incentivize more recycling.
Right.
It's programs that can allow easy collection and transport. We have to have the materials recovery facilities be able to efficiently separate the different materials in a quantity and quality that the downstream converters can work with. So, you know, with regard to mechanical recycling, you know, we need very high quality waste plastics to meet the requirements of mechanical recycling. maybe for chemical recycling, we don't quite need such stringent quality requirements. And so, but the point is, there needs to be a very tight linkage between the technologies that can convert the waste plastic and the technologies that can actually separate it and make it available to those, those processors to convert it. So we have to have a very holistic system view of this whole thing, right? And also even the brand companies that want, increased recycled content in their products, like soft drink companies and those sort of things, right? Everybody wants this to happen, but how do we put it all together, right?
Yeah.
And so I think we have to bring all of our expertise from the different parts of the supply chain and really figure out how we can do this.
All right, I'm going to put a big picture wrapper around this, and then we're going to keep taking questions.
Yes, please.
So I just want to make sure that I thank, while we still have 100 attendees, I want to thank Dr. David Shonnard, who is a chemical engineering faculty member, a professor here at Michigan Technological University, located in the Upper Peninsula of Michigan in the Pinky, and Dr. Felix Adom, who is one of David Shonnard's PhD students who graduated about 8 years ago and who is at Shell as a carbon strategy analyst, and I wish we had more time to talk about that, Felix. It's wonderful to even know that people are strategizing about carbon. There's a couple thank yous. There's a thank you from Connie Julian. Thank you, Dr. S. And there's a thank you from Dryson Geoghenan. Not a question, but thank you very much. I just want to...
Nice to hear my friends out there attending. That's great.
Yeah.
Well, and David Cour has a practical question. What's the downside to a landfill ban?
Right. That's a great question. The downside is that in the short term, it could be more expensive to find alternative end-of-life treatments for this waste material. And so I think I can certainly say from the European perspective that it costs more to treat these materials at the end of life rather than dispose of them. So I would expect in the near term, it would cost municipalities or counties or whatever more money to start up an infrastructure that we can then recycle the materials rather than the current infrastructure that we have for landfilling, right? So I think in the short term, the downside would be it would cost more, and so there would have to be some kind of incentive to make this infrastructure happen that we could recycle more.
Yeah, just to add to that, I mean, again, that perspective I think it's very fit for purpose for advanced countries, because I've also visited developing countries where landfill is like the only option, right? So they cannot do without it. So it's like until we have some infrastructure in place, which is I don't know how long that's gonna take. It's like the only option out there. So that's something to point out, I think.
Right, but I think there may be opportunities for pyrolysis and other kinds of conversion technologies to produce products that might be valuable to developing countries. For example, many developing countries use solid biomass fuels for cooking in open hearths, and that has terrible, terrible health effects.
Yes.
But if we could convert waste plastics to a gaseous fuel that's actually clean burning and make that available, that could actually be a win-win situation where we can help manage a solid waste problem, but at the same time provide clean fuels to these households that are using these kind of primitive fuels. So I think I agree with you, Felix, that landfill is super important, but I also want to keep open the idea that there may be sort of niche applications that we could deploy to take advanced technologies and make it work in those developing countries as a substitute for landfilling.
All right, there's so many questions. We've got to rip through some of these pretty fast. So do states with deposits on products have greater recycling?
Yes, so the bottle deposit program in Michigan, the recycling rates are very, very high for all kinds of packaging containers for bottles, whether it's aluminum cans or plastic bottles. So yes, very, very high return rates.
Are you familiar, this is from James Nuremberg, are you familiar with the hefty orange bag plastic recycling program in cities such as Boise and Omaha? How does that program work for recycling or energy recovery or other plastics?
Yeah, I think that I'm peripherally familiar with these kinds of bag programs, that they do tend to help create an environment where it increases plastics recycling. What I don't know is what happens to those bags after they're filled with waste plastics. You know, what happens to them then? Hopefully they don't go to a landfill. In previous years, they might have gone to China, but now they're not. And so we still need these technologies that can efficiently convert them to plastics again or other valuable products.
Well, and this is a question
Maybe a follow-up question on that.
Go ahead.
Sorry, because Dr. Shonnard, you mentioned incineration, because one observation, and I don't know whether it cuts across, is incineration to recover energy. It could be, I've seen models recover heat or steam. I've seen models recover electricity. What I've observed is the recovering to capture electricity often tends to reduce the emissions benefit. Is that your observation? Because even if you're going to energy, depending on what your target is, you potentially could, be losing your benefits. So
that's correct. That's a very good point. And that's something that we see in life cycle assessment. And the reason that occurs is because when you convert waste plastics to electricity, the conversion efficiency is quite low compared to the average grid. So if you're generating electricity and displacing the average grid, you're actually not displacing emissions necessarily. Right. So maybe generating steam or heat would be more efficient, where you can expect, I don't know, 80% energy efficiency if you generate steam, right?
Yeah.
So then this is where we kind of need the life cycle assessment to figure out, well, what is the best option, right? Is it electricity or something else?
Felix, I need your help. We have 31 open questions. So go.
Yeah.
Do you see on the Q&A? You can click on the Q&A, and then you can see all the questions. So I'm going to pick this question, and you pick the next question that gets answered.
All right.
That's good.
Okay.
All right. So this is a question from Kojo. For the plastics exported to China and Asia in general, what do they do with them?
Yeah, too often they become mismanaged, and they become, instead of recycled, they have to go to a landfill because the market is not favorable for recycling. And so they go to a landfill. Sometimes this is not managed correctly, and so the landfill, the monsoons wash away a bunch of plastic and it goes down the rivers, or a hurricane blows through and blows a lot of the plastic away from the landfill. So, these developing countries, they really struggle with how to manage these plastic waste at the end of life. Even though they receive it, they get it as an import into their country, they still struggle with it. So I really think the answer is that the developed countries need to manage it themselves and not export their problems to the countries around the world. We really need to manage this ourselves.
Great. So there's a question from Margaret. A few weeks ago, the Husky Bite was talking about recycling plastic to use in 3D printing.
Yes.
Do you do any work with that?
I do work with Dr. Pierce, but Dr. Pierce also is limited in terms of the 3D printing is a kind of mechanical recycling where you take the waste plastic, you melt it, and then you 3D print it. Every time you melt it and mechanically recycle it, the mechanical properties are degraded. So you can't do that indefinitely. So my point is we can work the chemical recycling, which has the potential to recycle it infinite amount of times because we create virgin quality plastic again, can work in conjunction with mechanical recycling. So if you're mechanically recycling a couple of times, you gain the benefit of low emissions and low energy and high profit from doing that. But then when the properties are degraded so much, now we need to chemically recycle it and create virgin material again.
All right, I'm taking the next one. This is from Tom Newhouse. Have you looked at soybean-based plastic? I used it in Iowa.
Yeah. So these are bio-based plastics, and so they're derived from plant material, from oils, plant oils, and things like that. and they can be converted into plastics, certain types of plastics, some of them biodegradable, others not necessarily. The one thing to keep in mind about bio-based materials is that they're not always more sustainable than fossil materials, right? I mean, I think Felix probably can back me up on that. It depends upon how the biomass is grown, how much fertilizer was used, right? The emissions from the land from the application of fertilizers, the processing of that biomass material to extract the materials that eventually get made into plastic. So, you know, it's a complicated set of conversions. And just because it's renewable and bio-based doesn't always mean that it's more sustainable. So again, we need to look at the whole life cycle and figure that out. It could be, but it isn't always.
Yeah, I have looked at that a lot, but I agree totally, especially if you're looking at first gen biofuels, I mean, feedstock, right? So if you're talking about second generation, like, you know, in fact, I did look at algal, you know, glycerol, right, which is a third generation feedstock. So in that case, you don't have the discussion of land use and all those things, but I agree totally with that point.
And the competition with food. If you can avoid the competition with food, then you're one up already.
Yep. So the next question is from Benjamin Kepes. He says, how does the process you are developing differ from the current plastic recycling process?
Well, the current plastic recycling is mechanical recycling. You basically take the separated waste plastic types and you melt them and you blend them and compound them in with virgin resin again. Maybe 10, 20, 30% mechanical recycled resin in with the virgin resin, and you can make a new plastic part again. So the chemical recycling takes it back to the feedstock again, to monomers, to these feedstocks that can go into a petrochemical plant to make new plastic again. So they can work synergistically, mechanical and chemical recycling, but really the potential for closed loop is with the chemical recycling technologies, because we can actually make virgin quality resin again, rather than working with the degraded mechanically recycled resin.
All right, so this next question, I think is maybe Felix, you can take a stab at this. What do you think is the best engineering major for an undergraduate student to choose if they really want to focus on tackling this problem of helping solve waste plastics?
I'm glad you have that question, Felix.
Yeah, it's. I'm going to answer it being biased because of my experiences. I feel I understand this better because one, I have a good chemical engineering background. Two, I've spent a lot of time around life cycle analysis trying to, you know, understand the carbon accounting process for all these processes. So if you ask me, I mean, my background currently is a very good fit for this area, which is chemical engineering with heavy focus on life cycle analysis, if that makes some sort of sense. Yeah.
That's a great answer. I'd also add to that, civil and environmental engineers are very valuable, because we do need to separate this solid waste material at the end of life and segregate it into different plastic types. So we do need, you know, civil environmental engineers. We need mechanical engineers, because these are all mechanical conveyance systems.
Yeah.
We need electrical engineers to sense the different types of plastics, so that in the material recovery facilities, we can separate one plastic from another. We need computer scientists who write artificial intelligence algorithms that help the robotics do the separation. I think pretty much all engineers, honestly. But
we also have economists in our teams, in my team at least, who looks at, you know, the cost of these new technologies and all this. So yeah.
And I would say we need social scientists too, to study the behavior of consumers and whether they will actually participate and recycle, right?
Yeah.
So this is one of these areas where we call it convergence science, right? Because we need the social sciences, we need the different engineers, we need the chemists, all at the table trying to figure this out, right? Because it isn't just chemical engineers to say pyrolysis, that's the answer. Well, it's part of the answer, but there's other parts that we don't have any idea about, you know, the social and the natural sciences and those sort of things. So,
well, and I would argue that people have a good, strong conscience about about caring for our planet. So here's a question. What about large items like broken plastic bins or broken plastic children's toys, or, those plastic children's climb on things? Landfill or recycle, other than duct tape, is there a way to repair them that an average consumer can try? And how do we with good conscience, how do we dispose of these things?
Right. Those complicated objects, fortunately, are not the high volume materials. Packaging, like I showed, was 39%, but we find plastic in cars and then machines and washing machines, and we find plastic even on houses, right? I mean, there's plastic everywhere, but really the high volume materials are the ones I think we need to focus on, because those are the ones that are the bottles that are washing up on beaches. Those are the ones that are hard to manage at the end of life. And I think those are the ones that have the potential to really contribute to increasing recycling rates. If you have a toy, yes, you can recycle it, but more importantly, recycle your bottles and your plastic bags. Those are the high volume materials.
A question from Olumide Winjobi. This should sound familiar.
Yeah, Olu. Hi, Olu.
It says, for the fuel grade closed loop recycling, what class of fuel is produced? Is it gasoline or diesel?
Well, depending upon the pyrolysis conditions, you can get anything from gasoline range up to diesel and even higher carbon numbers in the lubricant range. So really, as I mentioned in my talk, if you dial the reaction conditions appropriately, you can make pretty much anything you want.
All right, here's a quick one from Tom. HDPE and LDPE, so high density polyethylene and low density polyethylene, sound similar. What's the difference, and why do they have different recycling code numbers?
The difference is the crystallinity in the molecular structure, about how the polymer molecules align with each other. So a more crystalline polymer is the high density polyethylene, because they're more tightly packed, they're more dense, and they're more strong. The low density polyethylene is more amorphous, and it would be more like the flexible material, the flexible films and those sort of things are more of the low density polyethylene materials. And why the different codes? I think it's just a convenience to distinguish one from another in terms of their ability to recycle them.
Well, this question, maybe Felix, you can answer this one. Are some plastics more dense than water? I would assume those sink. Do plastics at the bottom of the Great Lakes or the ocean create a problem?
I think some plastics are more dense than water. In fact, most, right? From my experience.
Yes, polyvinyl chloride is one example.
Exactly, PVC is definitely, definitely one of them.
But I think also PET, if I'm not mistaken, is more dense because of the oxygen in that molecule.
PET, polyethylene terephthalate?
PET, yeah, polyethylene terephthalate.
Okay, I'm just trying to, where is it typically used so that the audience can relate?
That would be like your soda bottles.
Soda, yeah, okay,
or water bottles.
Water bottles, okay,
yeah, the small water bottles, yeah.
Yeah, okay.
So the answer is yes. I think that they do end up on the bottom of the ocean, and they do impact biodiversity at the bottom as well. So just because it's out of sight does not.
Yeah, if there's one thing we can do to help is to not buy bottled water, right? To bring around our, to use a glass, to use a recyclable jug. I mean, every time we do that, it's important.
Yeah, or use it and then recycle it.
Recycle, yeah.
Exactly. I mean, these are materials that can be readily recycled, and close the loop on them. So, I think there's multiple ways we can solve the problem. We can use less plastic by having alternatives, but honestly, plastics are such useful materials, like for transporting goods around in semi-trucks and so forth. I mean, plastics are very light. If we replace all plastic packaging for beverages with glass, then now we're burning more fuel in the semi-trucks that deliver it, right? So that's why plastics are very popular, because they're very useful, but they need to be managed at the end of life more efficiently.
Thank you. There's an interesting question. It says from Ward, it says, I believe helium is becoming more expensive and rare and saw it as an input to the vapor phase. Economic comments would be appreciated. So yeah, that's
Yeah,
an interesting one.
the helium was just it's a laboratory gas. It's inert gas for our
Yeah.
pyrolysis system.
Yeah.
We obviously wouldn't use that in a commercial scale.
Mhm.
So we might use a different inert gas, maybe nitrogen, or actually we would maybe want to not use an inert gas at all, but just use the vapor that's generated to drive the vapor out of the reactor. So instead of sweeping it out with an inert gas, maybe the vapor that's being generated continuously just pushes the vapor out that was there before. So, I mean, there's lots of different ways. We could use carbon dioxide, I think, as an inert gas rather than helium. So you'd want to use an inert gas that's very cheap and available if you had to use it.
Well, and this next question is from Stacy Seibold. How do the waste plastics need to be prepared, cleaned, cut down, before they can run through the pyrolysis system?
That's a great question. So we would want to separate the polyethylene from other plastics like PET and polyvinyl chloride. And then sometimes these plastics have food contamination on them or dirt, maybe labels that would like to be, so we would want to wash them and clean them and prepare them. So there would be an extra kind of pre-treatment step after separating the bottle, the polyethylene from the other types of plastic. There might be another cleaning step in addition to the pyrolysis, before the pyrolysis, right?
Right. Thank you.
Well, and we're coming up on the like 7:15 time frame. So Felix, you can pick one more question, and then I would love to just take a closing remark from each of you, starting with Felix and then ending with David. But let's take one more question first.
Yes. So Dr. Shonnard, there's an interesting question. This is a very great technology. I love it. This question I can relate to. Have you pursued any industry partnership, and particularly in relation to circular procurement and corporate social responsibility? In a follow-up to that is, why have industries picked this up, and if not, why?
Yeah, industries, in fact, there have been recently in the last year or two, some announcements, some very big announcements of joint ventures between very large petrochemical companies like Dow and BASF and other companies, maybe ExxonMobil, maybe even Shell, I'm not certain, with these advanced chemical recycling companies that can, using pyrolysis, can convert the waste plastic into a feedstock that the petrochemical companies can use. So there is growing commercial activity in this area. And the technology I'm working on, I believe has some advantages with low cost and high efficiency, and the ability to tune the reaction conditions to the products that you want, a tunable process. At this point, we're still very early in the commercialization. We don't have any partnerships with industry, but my team has gone through the I-Cour program, which is a innovation core program that the National Science Foundation offers. And so as part of that, we actually interviewed 100 potential customers. So we have lots of interviews under our belt, and we are looking to partner with one or more of these companies in the future, but we don't have a current partnership right now.
Great, thank you.
So, it's time for kind of wrap up remarks.
Okay.
First, just a few from me. My name is Janet Callahan. I'm Dean of the College of Engineering at Michigan Technological University, located in the Upper Peninsula of Michigan, surrounded by Lake Superior. Thank you so much for joining us. Michigan Tech is a wonderful place to earn an education, and it's been a pleasure to spend the evening with you. We've been joined by co-host Felix Adom, who earned his PhD with Dr. David Shonnard. Felix is now with Shell Corporation. And just some closing remarks from Felix and then from David, please.
Thank you, Janet. Thank you, Dr. Shonnard. Thanks so much for the invitation to participate in this session. It's been a very great session. Learned something new as always. I also thank Dr. Shonnard for the opportunity to study in his lab. I've been equipped with the relevant skills, and it's something that I'm really grateful for. But yeah, so as Janet said, I'm from Shell. I'm a carbon strategy analyst, and my focus is helping the company to navigate the energy transition and the challenges it brings with us. So really great session, and thank you again, and looking forward to connect at a future time.
Thank you so much for joining us, Felix. David.
All right, thank you. Well, first of all, Janet, thank you for the invitation to be on your Husky Bites program. And thank you to Felix for joining. I know how busy you are at Shell, and thank you. It was really a great pleasure to reconnect with you after so many years. And Janet, I just want to say, if there are outstanding questions that I can answer, I'd be happy to follow up. And if this could be made available to those who maybe want to come back in and view the video again, or if it can be posted on the Husky Bites website, I'd be happy to follow up and do answer the questions we didn't get to. I'll leave it up to
David. Do you want to can we share? Would you say your email address?
Oh yes, of course. drshonna @mtu.edu.
drshonna. Dr. Shonna at
Dr. Shonna. It's David, and my middle initial is R, so it's not.
All right, and
not
it's
meant
been posted.
To be doctor.
It's been posted in the chat. Well, and so thank you so much.
Just one final comment. You know, it's been my privilege to work with so many great students over the years. You know, they just come out of nowhere, really. I mean, I know they come out of somewhere, but you know what I'm saying. I mean, they come to Michigan Tech from all over the world, and they knock on my door, and we don't know each other, but you know, over the course of 4 years, we work together, and I see tremendous growth in the students. It's just so gratifying. That's the part that's just the best, to see, you know, how much they improve and they become professionals, and then they go off and do great things like Felix is doing in industry. So for me, you know, the technology is really cool, but it's really all about the students. It's really about watching them progress. And this is true for grad students and undergrads. I mean, I'm not trying to just silo it to grad students, but because we work so closely over such a long period of time, I really get to know the grad students more.
Yeah.
So that, I just wanted to say that I really, you know, I really owe everything to the students, honestly.
Well, thank you, gentlemen, and thank you, audience. We still have 60 attendees, and I'm ashamed that we have 23 open questions, but I just, I know from experience that people will stay on another hour, and I want to respect your time and our time. So thank you so much. Good evening. And, you know, it's a balmy 75 degrees outside or so right now. Believe it or not, it is. All right. Good evening. Thank you so much.
Thank you so much.
Thank you.
Bye-bye, everyone. Bye-bye. Bye, Felix.
Bye, Dr. Shonnard.